Welcome to Engineering Statics. This is a lecture on vectors versus scalars for Engineering ampersand 214 class in the Washington State Community College system. And we're going to talk about vectors versus scalars. In engineering mechanics, it's very important to be able to identify quantities like force and acceleration, moment, otherwise known as torque, and all of those quantities are what we call vectors. So scalars, you're probably used to working with from physics and maybe from chemistry. And the main difference between a vector and a scalar is that a scalar has units and magnitude. So an example of a scalar would be maybe .0 liters of water. We've got a magnitude of 1 and a unit of a liter, and then maybe a description of what the liter is. Something closer to home in engineering mechanics would be mass. So you might have 2.35 pounds or 6 kilograms. So you have, again, a magnitude and then a unit that defines what the magnitude is. Makes a big difference. A vector, on the other hand, is going to have all the things a scalar does, and then it'll also have a direction. So, and the direction is the big differentiating factor of a vector, characteristic, of a vector versus a scalar. So, when we say direction, that's kind of nice, but the most important thing we need to define the direction is a reference point. So anyone who has done any hiking or any kind of navigation is probably used to compass directions, north, south, east, and west. So that is an example of a directional coordinate grid that we could use that a lot of folks are familiar with. So if we started, say, at the origin and we went 5 miles east, and then we went 3 miles north. Each of these two changes in position is actually a vector. So we could say basically this first vector would be, it has a magnitude, 5, it has a unit, miles, and it has a direction which we could maybe describe as due east. Same thing over here. We've got a magnitude of 3, we've got a unit of miles, and we have a direction, which in this case is due north. And anyone who is familiar with, say, wind direction, often described, if you look on the National Weather Service, that you'll see little arrows on a map that will give a 10 miles per hour, say, in a direction that is so many degrees, say 30 degrees east of north in this case. So north would be 0, and if we go 30 degrees towards the east from north, we're at 30 degrees east of north. So that's another way of expressing, in this case, a wind velocity. So we've got, again, a magnitude of 10 units of miles per hour. That's pretty good stiff wind. And a direction, 30 degrees east of north. So another way of expressing direction, which y'all might have seen in trig, in fact I hope you've seen in trig, is the unit circle. So we can define, again, we'll start with a little coordinate system. So we can say 0 degrees is on the right and 90 degrees is straight up, where north would have been 180 degrees and 270 degrees. So if we have a vector, we can give it a length and then give it a direction around our our unit circle. Well, 0 is also 360 degrees, otherwise known as 2 pi. So we could have, say, we could have 10 feet in a direction of, that looks like about 120 degrees. Now we don't have to reference east of north or anything because a 0 degrees pointing straight to the right is our reference direction. So all we have to do is say 120 degrees, and that defines this vector. We can call it vector A. And when we name a vector, one way to tell everyone, if we're just writing something as a vector A, we don't have to call it vector, we don't have to use the word vector. We either put it in bold type, which I can't really do here writing on the board, or I just put it in regular type and I put a little arrow over the top. So either a bold A or an A with an arrow over the top denotes that it is a vector, which means in addition to a magnitude in units, which a scalar would have, it's also got a direction in some coordinate system. So the most useful way of describing vectors, and it's the one that we will use the most in statics, is with reference to a coordinate grid or a coordinate system. So everyone is used to graphing and having an XY graph or an XYZ. So we're gonna use a 3D coordinate system. And this follows what's called the right-hand rule, which we'll learn more about with a cross product, but hopefully most folks are familiar with this, where we've got X coming out in this direction, and at right angles to it we've got the Y-axis in this direction and the Z-axis in this direction. And we often denote the X-coordinate direction by a unit vector I, and that's just convention. And a unit vector, which is something we'll learn more about in a future lecture, but I'll give you a little hint because the coordinate axes are defined this way and it's super handy. It's a vector that has a magnitude of 1 and no units. So it's always a length of 1. It can be pointing in any direction you want, but it's got a magnitude of 1 and no units. So I hat, and that's what the little caret on top of the letter means, signifies the x-axis, no length. So we can either say the x-axis or we can say I hat. So if you want to say you've got a vector of 5 feet in the x-axis direction, you can just say 5 feet I hat. It's a lot easier. And by the same token, the convention for the y-axis is j hat and the z-axis is k hat. So I hat, j hat, and k hat are unit vectors pointing in the directions of the x, y, and z axes respectively. Now we can define direction as going over so many steps or so many positional units, so much length in any one of these directions, and kind of go over, across, up, down, and define our path that way. And then the angles with the axes will be whatever they end up being. So let's just walk one out. Say we start at the origin and we go 1, 2, 3, 4, 5, 6 units in the I hat direction. And maybe we'll call that 6 meters. So we could call that vector A. And then we have another vector B, and we'll put it in another color. And it's going to maybe go, I don't know, 8 units. Just in the j hat direction. And just to keep things 3D, we're going to make something that goes way up. C, that is, say, 10 units. Okay? So an easy way of representing this in terms of our unit vectors that define our axes, we can say, all right, vector A is, we said it was 6 meters. We're going to say it's 6 meters in the I hat direction, which means it's 6 meters going in the x direction. And vector B is, it said it's 8 meters, so it's 8 meters j hat. And vector C is, we had said it was 10 meters long, and it's heading in the k hat direction. So you can see the I hat, j hat, k hat is a little bit like saying east, south, north, but it's our good old familiar mathematical XYZ Cartesian coordinate axes. So we can define our vector direction by referencing our x-axis, y-axis, z-axis and say, how far did you go in each direction? And so that's an alternative way of denoting the direction component of a vector. And as you'll see, as you start to get into 3D and a whole lot of vectors adding up, it's a lot handier than necessarily having to resort to your trig and just doing things with angles. But, of course, they're related. So let's go over here to the side and let's just take a little slice of our 2D XY axis here. We can use trig to pull these two systems together. So let's write our unit vectors on a little coordinate axis here. And let's draw a vector from the origin at some angle. And we'll call this vector F, because that makes it sound like a force, which we're really concerned with in statics. We really like force vectors in statics. So this is pointing at some angle, theta, with respect to our I hat or x-axis. It's pointing with it's at an angle of 90 degrees minus theta to the j hat or y-axis, which we can get from the definition of right triangles. Our coordinate axes are at right angles to each other. We can go from a theta and a length. We can say that our force vector has a magnitude, right? It's got a length, a magnitude of just F. So there's another definition that we've kind of segued into the magnitude of a vector F is denoted by the vector symbol in vertical lines, kind of like the absolute value symbol, or you can just simply write it as F without its arrow, because of course a magnitude is a scalar. When we write vectors, we can symbolically denote their magnitude by their physical length on a paper. Sometimes we don't. Sometimes we just write their magnitude, and we will be using other dimensions on a coordinate axis just to figure out which way they're pointing. But one way of representing a vector magnitude is the length on a representative scale drawing. So say we're going to assume that the physical length on our little piece of graph paper here of vector F, regardless of what it's actually representing, but will represent its magnitude by its actual length here. So we can find the components of that vector with some trig. Say I wanted to ask myself, hey, I want to know how much of that total magnitude of vector F is pointing in the I hat direction and how much is pointing in the j hat, and I want to be able to write some expression for the vector without having to refer necessarily to angles of, theta degrees of, clockwise of x or whatever. I can use my unit vectors for the axes to write an expression for vector F in terms of how much of it is pointing in the x direction or I hat direction and how much of it, like this component, and how much of it is pointing in the j hat direction. So boy, that looks like a right triangle to me. So I know that I can use good old Sakatua from trig to get the components that I need. So I can represent my full vector as the magnitude of the whole thing times the portion of that magnitude pointing in this direction. So I get that with cosine theta, of course. So f cosine theta is the portion of the full magnitude of the vector that is pointing in the I hat direction. Now we've just made a little subcomponent vector because we got a magnitude and we'll have a unit somewhere there on that f. By putting that I hat designation, I multiplied this scalar, this f cosine theta, which is a scalar, by a little unit vector. So this component here is itself a vector. That's cool. But it's not all of what makes up f. F is more than just this. This is just the part going in the x direction. So I can use a little more trig, and I can write the portion going in the y direction. So I've got the full magnitude of f times sine theta, which captures just the portion that's going in the j hat direction. So now I have an expression for vector f in terms of my coordinate axes. And this is super handy because I can add together components that are heading in the same direction. So if I wanted to add this force vector to another vector that was heading in another direction, say vector q, I could find the components of q, say qx and qy, I don't know what they are, but I'll just call them q sub x heading in the I hat direction, which is probably going to be a negative number, and q sub y heading in the j hat direction. And I can write an expression for algebraically for the combo, the sum of those two vectors, just by summing the portions of each that are going in the same direction. So I can add all the components that are heading in the I hat direction together, and I add all the components that are heading in the j hat direction, and then designate those by their unit vectors. Got to group them together. So I could have something like q sub x, which, like I said, I figured that's probably going to actually be a negative number, plus f cosine theta, all pointing in the I hat direction, plus q sub y, plus f sine theta, all pointing in the j hat direction. This is a very handy way of adding and subtracting vectors. And the nice thing about this is the representative length on a page doesn't necessarily have to correspond to the vector magnitude. You don't have to draw it out and add it on paper. You can add it algebraically. Now, that said, if you represent the magnitude of the vector with the length of the arrow on the paper, we do have some powerful rules for adding vectors together that kind of give you an idea of what's going on. So this is kind of, I call it the graphical way of adding vectors. So if you've got vector A here, say, and you got vector B, this is called the tip to tail way of adding vectors. And this is sometimes useful for mapping and cartography. So you might head so far in this direction, and this is sometimes useful if you've got a say a reference direction. So say we are assuming that this direction to the right is like maybe say a 0, right? That's a 0 degree compass direction. So we know we walked 10 miles at 45 degrees, and then from there we walked 30 degrees west of north, 6 miles or something. And what is our total displacement from our start? Well, we would simply add vectors A and B. Add them. Drawing a straight line there, freehanding it for vector C. So that is called the tip to tail method of vector addition. So if I wanted to say what is vector A plus vector B, if I wanted to do it graphically, I would just take the tail, the tail of vector B and add it to the tip, meaning that the arrow of vector A, to get vector C. Now, hidden within here, we've actually got our I hat, J hat kind of algebraic, addition hidden within, because we could take a look at vector A and go, well, what we've really got here, I'll try to get my red pen back. I've really got, I've got an A sub x heading, straight in the 0 direction, and then I go up A sub y, and then for vector B, I'm continuing to go up B sub y, and then I'm going back west B sub x. I'm assuming we're... If I were to take vector C and create only, kind of the east, west, north, south components of it, cy and cx, I would find that cy equals by plus ay, and that cx equals ax minus bx. So we can do the graphical method of vector addition if our vector magnitudes are represented by the physical lengths of our arrows, and we can still apply some trig with our angles and get components in orthogonal directions. They have to be at right angles. Trig works really well with right angles. And then add them all up, and that's the same as adding up all our I hat, J hat, K hats when we use our coordinate axes unit vectors. It's effectively the same thing, but a little bit different way of representing it. We will be using the I hat, J hat, K hat system most of the time here in statics. But when you take other classes in vector addition, or if you do any work with cartography or surveying, if you're going to head into civil engineering, you may see this coordinate system where you have a reference angle and you're representing your vectors as in terms of magnitude and direction with reference to a coordinate angle. You can add them up the same way. Trig works in both cases. So that is it for this mini lecture on vectors versus scalars. Ways that we can represent vector magnitude and direction, either with unit vectors on a Cartesian coordinate axis or with reference to a single reference angle, how we can add vectors either kind of tip to tail graphically or in terms of our I hat, J hat, K hat, I's add to I's, J's add to J's, K's add to K's, and we can add vectors however we want. Oop! Last quickie, how do we subtract vectors? We just add the negative. So if I were to say f minus q, just like a scalar, I would just simply say negative q sub x plus f cosine theta I hat plus etc. So I would just put a negative sign, and in the case of our graphical representation, if I'm adding vector A to vector B, like so, to get vector C, If I wanted to subtract vector B from vector A, I would just add the opposite. And I could simply advance it down its line of action. I'd turn it around, add the negative, negative B, and now my resultant is pointing in this direction. So subtracting a vector is like adding the opposite of a vector or adding that vector flipped and heading in the opposite direction down its line of action, which if you're using your coordinate axes notation, all you have to do is put a negative sign. So you can add and subtract vectors now. So next videos we'll discuss vector multiplication via the dot product, which is something that you'll use to get portions of vectors parallel to each other. So stay tuned.